Okay, number one of the three response section of the practice problems. Should be starting to look pretty familiar. We've got, I think we did this one maybe even in class. We've got a guy, case A and case B, he's riding in an elevator with a scale again. In case A, he's moving up at 3 meters per second and accelerating up at 2 meters per second squared. In case B, he is moving up at 3 meters per second and accelerating down at 2 meters per second squared. Again, just to review a little bit of kinematics, we could say, okay, if he's going up and he's got some initial velocity and he's accelerating up, right? That could be my VT. And over here, he's still moving up, but he has a negative acceleration. So I think we talked about this in class, that the fact that he has some initial velocity has nothing to do with this problem, right? The fact that he's accelerating up and accelerating down has everything to do with the problem. I know this is not the way we were supposed to do it, but I'm going to use these little pictures as my basis for the free body for now. So first of all, we know that we have a weight vector here, and that weight vector should be the same in both cases. It's the same guy in the same elevator. Force of gravity is the same. But on the left, if he's accelerating upward, then we know that the scale force has to be greater than the weight. And if he's accelerating downward, that the scale force has to be less than the weight. And we can prove that. Newton's second law says that in order to have an upward acceleration, you have to have more force up than down. So the scale force minus the weight has to equal ma. So the only way that the a is positive here is if the scale force is bigger than the weight. Over here, same equation. And again, one of the big issues is we want to think that, oh, do I put negative in for A? We let that equation dictate what must be true, right? This is a universal equation for this elevator. You notice the left and the right look exactly the same. So on the right, if the acceleration is negative, then it means that mg must be bigger than the scale. So here it says, will the scale reading be greater, less, or the same as in case B? Well, the scale reading has to be, so let's write it. Scale reading equals ma plus mg. If a is positive, then I'm going to get a value there that's bigger than mg. Over here, I get scale reading equals ma, same thing, plus mg. But if a is negative, then I'm going to be subtracting that term from mg, and the scale force is going to be less than his weight. So that was, I think we did that on one of the first days, but by now we should be able to really kind of explain and talk about everything going on. This isn't about solving and coming up with an equation. It's not about the equation. It's about understanding what Newton's second law really says, that to change your motion, right, which is what we define with A, you have to have forces that are not balanced, which is what we do with some of the forces. Those are vectors. Okay, the next one here. This is a lot of reading. So we've got a couple of objects attached by that string in the middle, 6 and 10 kilograms, massless wire. So we have a constant acceleration. I'm going to write that over here so we don't forget. Acceleration is downward at what, 2, 3. Be careful, that's not a force vector. That's just an acceleration vector, so I can remember that it's accelerating down. The result is a constant acceleration because the force F is smaller than the total weight of the objects. The tension in the wire connecting the object is T, and then we have a discussion here about what these students say about these forces. Okay, so let's start before we read. These Anne and Brandon and Kathy and Deshi have some interesting things to say about this. But before we do that, maybe we let's get a better idea of what's going on ourselves. So let me me steal that. So I'll steal it all. Okay. So let's diagram this system out. And we'll do two diagrams. Again, we have two objects. So we have, let's put M1 there. And let's put M2 there. So M1 is on the top. So that means, remember, F is only acting on M1, even though we know it's responsible for lifting both. That's why we separate the diagram, because these are contact forces. So I have two forces, T and whoops, I called that M1. T and F. That's it. Over here on M2, the only force I have on it, whoops, I have another one. And that's M1G. So I have three forces, F, T, and the weight. Over here I have two forces on this one. I have the force T acting up, and I have M2G acting down. And don't forget, our acceleration is down. So let's write this out in the form of an equation. So we could say the sum of the forces has to equal M1A. So that means F minus M1G minus T equals M1A, right? Over here, I could say sum of the forces has to equal M2A. So T minus M2G equals M2A. And if you had me in class and we were talking about Atwood's machines today, and you remember that we reversed, we did an Atwood hanging over a pulley, recognize that this doesn't apply. We wouldn't change the signs and make one up and the other down, because this is both objects are moving up. There's no redirecting of forces with a pulley here. So now I have F minus M1G minus T equals M1A, T minus M2G equals M2A. Let's go back and see if any of these statements make any sense. The tension is the net force on the lower object, which is 30 newtons. So we have values here. I guess we can maybe look at some of these values. This was 6 kilograms, is that right? M1 is 6 and M2 is 10. 6 kilograms, 10 kilograms. We also know the acceleration is 3. So we can actually start to kind of look at some of this stuff. F minus 60 newtons minus T equals 6A, right? Just plug the values in. T minus 100 newtons equals 10A. Okay. So that means T has to equal 10. I don't know why I made that a capital A. 10A plus 100. So I can work all this in. F minus 60 minus 10A minus 100 equals 6A. Notice I made the 10A and the 100 negative because that's negative T. So I distributed, kind of thought about parentheses being around that, distributed that around that. So F minus 160 newtons has to equal 16A. If that makes any sense. Yes. Okay, so the tension is the net force on the lower object, which is 30 newtons, since net F equals ma from Newton's second law. The lower object has a mass of 10 and is accelerating at 3. So is that true? If the lower object has a mass of 10 and an acceleration of 3, then Newton's second law says yes, it does require, oh, you know what, I knew that. I know the A there, so we could say F minus 160 equals 16 times 3 is what, 48 newtons. So F has to equal 208 newtons. Makes sense. And then T has to equal, where's the easiest one for T? T equals, just plugging and chugging now, T equals M2 A, which is 10 times 3 equals 30 newtons plus 100 equals 130 newtons. Okay. So Ann's onto something by saying that there has to be 30 newtons of net force acting on it, but the tension is not the net force. The tension is the difference between, or the net force is tension minus weight. So since this object weighs 100 newtons, the net force is 30, so the tension has to be 130. So Ann doesn't make a lot of sense. Although some of the stuff is okay. It does require 30 newtons of net force, but she's not accounting for the weight of the object, which is already 100, so T has to be 30 more than 100. No, the tension is more than the net force of 30. Since the lower object has a weight of 100, the tension should be 130. Okay, Brandon sounds like he's on to something there. That's exactly what we just said, that if the M2 weighs 100 newtons, and Newton's second law says that M2 needs 30 newtons of net force, then T must be 130. Let's see what Kathy has to say. You are both wrong. Sounds like a Kathy. The tension in the wire is upward and should be less than the weight since the system is accelerating downward. The tension in the wire is upward and should be less than the weight since the system is accelerating downward. Is that true? That sounds like a pretty good statement, right? The tension should be less than the weight. However, it should be 70 newtons by applying Newton's second law. You know what? I think Kathy's right. We made a mistake here. Sorry, Kathy. I didn't give you enough credit. I just realized my mistake. This proves to you that I don't do these ahead of time. I forgot acceleration is negative here. So this is A is -3, so I have to say F minus 160 equals -48. So when I move that aside, it would be 160 minus 48 is 112. Right, and then the tension would be T minus 100 equals -30. So this has to be 70 newtons. Sorry, Brandon, but you were close. Brandon was close, but negative acceleration means the downward force has to be bigger. Kathy's now on top. And then Deshi he's certainly confused. I don't think we can answer it until we know which direction. Remember, it isn't about which way it's moving, it's about which way is the acceleration. Something can be moving upward or downward and still have a negative acceleration. And forces are all about acceleration, not simply velocity. It's about changing velocity. So sorry, Deshi. So we're going to agree this time with Kathy. And we've explained that in lots of detail. But essentially, if this system is accelerating downward, and all these we didn't have to do really as much as we did, but T has to be less than the weight of M2. So Kathy's the only one that makes sense. And then when we solve that, two equations, solving it for F and then T, we get 70 newtons of tension because the weight of M2 is 100. And if we look at M1, M1's only 60, but it's accelerating down, so now tension plus 60 minus F gives me the same thing.